So far this chapter is focused on hypothesis tests about a single population mean. Although many decision problems involve a test of a population mean, there are also cases in which the parameter of interest is the population proportion. The basic concepts of hypothesis testing for proportions are the same as for means. The null and alternative hypotheses are stated in terms of a population parameter, now p instead of mu, and the sample statistic becomes p bar instead of x bar. The null hypothesis should be a statement concerning the parameter that includes the equality. The significance level hypothesis determines the size of the rejection region. And finally, the test can be one or two-tailed depending on how the alternative hypothesis is formulated. Remember that when dealing with proportions, we are working with categorical values where there are two possible outcomes, or success and failures as we define them. Some examples we've had were scored shots to the basket per game, or defective items manufactured. Also remember the requirement that sample size n is large such that n times p is greater than or equal to 5, and n times 1 minus p is greater than or equal to 5. Alright, so in this case, some league is considering increasing the season ticket prices for basketball games, and the manager is concerned that some people will terminate their ticket orders if this change occurs. So here, if more than 10% of the season ticket orders would be terminated, the marketing manager does not want to make this decision to implement the price increase. So our claim is that P, the population proportion, is less than or equal to 0.10, and the alternative would be that P is greater than 0.10. So here we've set alpha to be at 0.05, our x is 14, and n is 100. So at an alpha of 0.05, our z critical is 1.645. So we can calculate a p bar critical such that p 0.10 plus our z times p times 1 minus p over 100. So our p bar, or sample proportion, is 14 out of 100, or x divided by n, so that's 0.14. So we'd say 0.14 is less than the p bar sub alpha of 0.149, so we will not reject the null hypothesis. Alternatively, we could compute a p-value off of p bar of 0.14 and compare that to alpha. So in this case, we would expect to have some sort of p-value greater than or larger than our alpha of 0.05. Alright, go ahead and open the Excel file Echo and answer the following questions. So since the manager recently stated that less than half the warranty returns are wiring related problems, we will use that to formulate the null and alternative hypotheses. Alright, so here our null hypothesis is that p is greater than or equal to 0.50, and the alternative is that p is less than 0.50. So to determine our p bar, I'm going to insert a pivot table. So to calculate our p bar, we'll take our 23 for wiring divided by the 110 to get a p bar of 0.209. So we'll compute the z-calc by taking our p bar minus p and dividing by the standard deviation. We can also compute our z critical value by using norm.s.inv and 0.02 being the lower probability. So since negative 6.1 is less than negative 2.05, we're in the rejection region and we will reject the null hypothesis. And again, we could also compute a p-value for our z-calc. So if we compute a p-value using the norm.s.dist function, we get an extremely small p-value, far less than our alpha, so it's obviously in the rejection region. Okay, thanks for tuning in. That was section 9.2.